We are now getting ready to get right into Chapter 1, which is where the newer material is. Section 1 is kind of a transition in that it's kind of showing you how pre-calculus becomes calculus. So it's an introduction to calculus. Calculus is the mathematics of change, but at the same time, there's more to it than just that simple definition. What it does is it uses a process known as the limit process to take topics that we study in pre-calculus and change them kind of into topics of calculus. Whereas in pre-calculus, everything is considered constant. Calculus is more considered instantaneous. So we'll look at some of the differences here. I have 4 of them listed. Notice here that the first one talks about constant velocity, which is a lot like slope, and we talk about that as instantaneous velocity. For example, if I drive for 2 hours and I go 120 miles, then I'm gone a constant velocity of 120 divided by 2 is 60 miles per hour. But did I travel 60 miles per hour the whole time? Most likely not. I might have sped up, I might have slowed down, and so I might be interested in what my velocity is at a particular instant as compared to over the 2-hour span. So we use this limit process to change constant velocity into instantaneous velocity. Also in pre-calculus, we talk about the slope of a line. Well, the slope of a line is good because it's constant. It never changes. No matter what 2 points you take on the line and you use the slope formula, you get the same value. You get the same number as long as it's non-vertical. Well, now what we're going to do in calculus is we're going to use kind of that idea along with the limit process, and we're going to change this into the idea of the slope of a curve. Now, the slope of a curve sounds kind of weird, but as it turns out, the slope of a curve has to do with the slope of the tangent line to the curve at any particular point on this curve. Speaking of tangent line, pre-calculus, we have a tangent to a circle, but in calculus, we have, and of course, that's the line that is perpendicular to the radial, or the radius that's drawn on that circle to the point of tangency. We talk about the tangent of a general curve. Okay, and then the last one is a little different. It's talking about the area of a rectangle and how we could use the area of a rectangle along with the limit process to find the actual area under a curve. Pretty much the only curves that we know how to find the area of are circles, or perhaps part of a circle like a sector. So we're going to take many of the pre-calculus topics, and we're going to use this limit process, which we're going to define more in the next section, and we're going to come up with calculus topics. Now, there are 2 branches, main branches of calculus. We'll study differential calculus first, and that has to do with the idea of what we call a derivative, and then we'll study integral calculus, and most of that comes into play right at the end of the first semester and into second semester. Integral calculus, which involves the main idea of an integral. Now, both of these 2 branches can be introduced, which I'm going to try to do just very generally here, with what they consider one of the classic problems of calculus. And the first classic problem introduces the idea of differential calculus, and it is known as the tangent line problem. Now, you need 2 points to find the slope of a line. If I am attempting to find the slope of a tangent line, I only have the 1 point, the point of tangency. So to find the slope of a tangent line, I start out by looking at a second point that's on the curve, which I'm going to call over here, I'm going to call this point, the point of tangency being point P, and the second point being point Q, and I am going to find the slope of that secant line, which I'm going to draw here in red. And the slope of the secant line can be found by taking, using the slope formula, that the slope of the secant line would be equal to the difference in the y values over the difference in the x values. So I'd have f of a plus delta x minus f of a all over the difference in the x values, a plus delta x, minus the x value there, which is a. And of course, you can see that these a's cancel. And I end up with f of a plus delta x minus f of a all over delta x. Now, that guy should look familiar from back in the prerequisite chapter. We called him the difference quotient expression there. And we are going to find the slope of this expression using the limit process. Now the solution to the slope of the tangent line was solved by a mathematician whose name I have been mispronouncing for many, many years. I've been pronouncing his name as Pierre Fermat or Fermat, and this happened back in 1621, but I looked it up on the computer, and if you listen closely, you'll hear the computer pronounce his name as
Pierre Fermat.
Pierre Fermat.
Pierre Fermat.
Yeah, I've been doing this guy an injustice for probably more than 35 years. I apologize to him and his family by mispronouncing it, but he uses this idea of the secant line. Now, look at the way I've got this drawn. I've got A here, and instead of giving this a value called like B, I call it A plus a little bit more delta x, which is this distance here is delta x. So what we are going to do is we're going to look to see what happens as if delta x gets smaller and smaller and smaller and approaches 0. Well, if delta x is getting smaller, then point Q is moving along the line, along this curve. Maybe I move it to here. Now, if I try to draw a secant line between those 2 points, you're going to see that it's going to be slightly different. I'm going to try to draw it here. And the secant line has a slightly smaller slope in this case. Well, eventually what I want to do is I want to continue to move point Q along the line so it gets practically right at point P, because what am I trying to do is I'm trying to find the slope of the tangent line, which I've got drawn here. Hopefully the tangent line looks like it's drawn here in green. Well, as I move this point along this curve, my red lines here, my secant lines, are going to get closer and closer and closer to becoming the green line here, which is, as you can see here, or at least it's supposed to be representing the tangent line here itself. So we'll kind of get into this into a little bit more detail starting in chapter 2, but this is the tangent line problem using and approximating the slope of the tangent line using the slope of the secant line. All right, now the second branch of calculus, or integral calculus, uses a different classic problem. It's the area under a curve. Now, let's see if I can draw this in here for you. Here's a curve, y equals f of x, between x values of a and x values of b, and I'm interested in finding the area of this region right in here. Well, to do that, what I'm going to do is I am going to break up the interval from a to b into smaller subintervals. This is known as partitioning the interval, and I'll just break it up into a little bit smaller ones here. And I'm going to try to draw it so that all those subintervals look like they're the same size. I have 1, 2, 3, 4, 5, 6. I have 6 subintervals here. Now, if I was to draw vertical extensions here from each one of these points, and I'm doing this in green here. I hope that this is legible in the video. And what I'm going to do now is I am going to inscribe rectangles, because I know how to find the area of a rectangle. That's base times height. But I'm going to inscribe rectangles here, and I hope that you will agree that if I was to find the area of each one of these 6 rectangles and add those areas up, it would be an approximation to the area under the curve. It would be an under approximation, because you can see there's some space here in each one of these rectangles. Well, apparently the trick is 6 rectangles isn't enough. Let's say instead of 6 rectangles, I had 12 rectangles, or 60 rectangles, or 600 rectangles, or 6,000 rectangles by partitioning it into smaller and smaller pieces. All right, that partition, breaking it apart, would give us if we let the number of subintervals increase, would improve my approximation. So I am going to find the area of each one of these rectangles, add them together, and use that to approximate this. Well, as it turns out, if I use the limit process, if I let n, the number of subintervals, get big without bound. If I let it go to infinity, then I have the exact area under the curve. And this is involving a limit process again. It's just a slightly different limit process than the one in the tangent line problem. But this will help me to bring in the idea of what we call an antiderivative or an integral, and that starts off with us with the second branch of calculus, the integral calculus. So I have a few problems that are good examples that are assigned for you to use that are kind of based on this idea, but my suggestion would be, after listening to this video, is that you look at some of the examples that are drawn out for you also in the textbook before you get started on the problems.